Hello once again, class. Welcome to another mock lecture. Today we're just going to get right into the law of sines here with a little bit of motivation for why we need to know this. So we've been working with right triangles up to this point, and as you might know, right triangles are really nice. They're easy to use. You can construct them based on coordinates given in the Cartesian plane. We can find all the trig functions if we know one of them and then another one, whether it's positive or negative. And then they're really easy to use as far as like word problems go, right? If you want to find the height of something, then you just need an angle of elevation and a distance away from the object, right? And that's it. But here's the thing. Oftentimes in your real life, you're not going to have right triangles to work with. We might not be able to construct a right triangle for whatever reason, and so we're going to need to know how to solve for lengths and angles of triangles that aren't right, which, by the way, are called oblique triangles. So an oblique triangle, stipulated definition, very straightforward. It's a triangle that is not a right triangle, meaning it's a triangle that does not have an exactly 90-degree angle measure. So like right triangles, right? There's still some similarities. You have to know some stuff about it in order to be able to solve the specific triangle. In a right triangle's case, you typically only need to know like one angle, and I guess technically you'll know two of them because one of them is a right angle, and a side. So you need one angle that's not the right angle and then a side, and then you can pretty much solve the right triangle. Well, you need about that same amount of information to solve oblique triangles, except that we don't get one for free, right? We don't have a right angle to use our trig functions, based on inside the triangle. So you have to know some stuff about it. Like here's an example of a triangle where we don't know some stuff about it. We know two things, I guess, about it, but this is not enough to solve an oblique triangle. You very typically need 3 pieces of information. This one only has 2. And on top of needing 3 pieces of information, you typically need them in a specific type of configuration as well. So like, for example, we can't really solve a triangle when only the angles are given. Right, we wouldn't know what any of its side lengths are. We need some kind of, setup. We can have all the angles, that's fine. And if we know one side, right, then we're going to be able to solve that triangle because now we know kind of what the scale of the triangle should be since we're given a side. But if you're just given all the angles and it says solve the triangle, well, there's an infinite number of solutions for something like that, right? You could have, one of your sides be 3. Right? Or you could have that same side be 10, right? And it could still have all the same angles, right? You just have similar triangles if you're comparing the two. So oftentimes you need to know something else, right? In this example, I'm giving us an angle and 2 sides. This is a situation where we would be able to solve this thing potentially. This happens to be one of the cases that's most difficult to solve, but it is something that we could look to solve using either law of sines or law of cosines, which are the 2 main methodologies for solving oblique triangles. And remember, I don't know if I said this, but I'll say it again, that solving triangles is knowing all the sides and knowing all the angles, right? Then that's a solved, quote unquote, triangle. Okay, now there exists 4 cases, 4 configurations of 3 given pieces of information that we would be able to solve oblique triangles for. The first one is called a side-side-side situation. If you know all the sides of a triangle, you're going to be able to figure out what the rest of the angles are. Right, you're going to be able to figure out what the angles of the triangle are. If you know the sides, that's the side-side-side triangle. There is only one solution that you're going to find. That's what unique solution means. There is only one triangle that has side lengths 7, 8, and 12, and it's going to be whatever the specific angles are when you solve them. Okay? There's a side angle side situation, and that's when 2 sides and the angle that is between them are given. Again, this presents a unique situation. There is only one triangle that has these specific measurements for a side, an angle, and a side, meaning this will always give you the same number, right, when you solve this. This is another law of cosines situation. So we're not going to be talking about these 2 cases for today, but we will be covering this in another video using the law of cosines. The law of sines situations, right, the 2 that we're going to be solving with the law of sines, starts off with the angle side angle or angle angle side situation, which is kind of a disguised, we actually know all the angles and one side. Because think about it, if you know 2 angles, which we do in these cases, in a triangle, you would know the last angle by just subtracting the sum of the 2 given angles away from 180. Right? So we can always figure out what the last angle is in an angle-angle side or angle-side-angle situation. So it's kind of a disguised, actually we know 4 pieces of information. We know all the angles and a side, which gives us the scale for the triangle, so then we'd be able to figure out what the other sides are going to be. Again, this presents a unique solution, and it's the one that we're exclusively going to be talking about for today, because the 4th case deserves its own video. The 4th case is side-side angle, and it's when you have 2 sides and an angle that's given. It doesn't matter the orientation of them. It's just 2 sides and an angle. Although, to be fair, it can't be the angle between the 2 sides, because that'd be a side-angle side situation, and then you would be able to solve that with the law of cosines. So the angle can't be between the 2 sides that is given. So it's one of the other 2 angles. That's a side-side angle situation. And the problem is that there is not a unique solution many times for this sort of situation. It's possible there's actually no solutions. You could actually have a side-side angle situation with no solutions at all, because the 2 sides and the angle that's given actually don't even form a completed triangle. It's possible that there's one solution, but it's also possible that there's more than one solution. It's possible there's 2 different triangles that both satisfy the side-side angle situation. And it's because of this ambiguity that we don't really know what's going on until we start analyzing it more. Side-side angle case is oftentimes called the ambiguous case, because it's ambiguous. By just looking at what's given, side-side angle could have 0, 1, or 2 solutions. And we're going to dedicate a whole video to side-side angle triangles. But for today, we're going to be working on this one, and we need to know the law of sines to be able to solve angle side angle, or angle angle side. So let's go through deriving the law of sines. You guys have been watching my videos long enough. At this point, you know I don't just like to give the formula away. I like to show where it comes from. So we're starting off here with what's called the standard labeling of a oblique triangle. And I think we've talked a little bit about standard labeling before with right triangles, and it's basically the same. The only difference now is there's no right angle, and side C is opposite angle gamma. But otherwise, beta is always opposite side B, alpha is always opposite side A, and then we label the vertices A, B, and C, and they have alpha, beta, and gamma as their vertex angles. Okay, that's standard labeling. What I'm going to do is I'm going to drop an altitude without loss of generality from vertex B. So I could do the same thing where side A is the base, and then I'd drop an altitude from vertex A. I could do the same thing where maybe C is the base, and then I would drop an altitude from vertex C. It doesn't matter. The law of sines gets derived the same way. In this case, I just happened to write the standard labeling where AC is the base of this triangle. So the altitude is a height that goes from a perpendicular intersection from base AC to the vertex B. Okay? And I just want us to notice, we've created 2 right triangles here. One of them's here, right? One of them's here. The sine of alpha's here, is opposite over hypotenuse. That's H over C. The sine of gamma is H over A, right? Opposite over hypotenuse. Now, if I solve both of these things for H, we get that something's equal to H, in this case C times sine alpha, and something else is equal to H, in this case A sine gamma. Now, if you have 2 things that both equal H, that means that the things that equal H are also equal to each other. That's called the transitive property. So I'm going to say, okay, well then this means that C sine alpha is equal to A sine gamma. Now I can manipulate this by dividing both sides by C and A to get this proportionality, and it's that proportionality that encompasses the idea behind the law of sines. Basically, if you can link some kind of side length with the sine of its angle that it is opposite of, that sets up a ratio for all of the other sides, which is pretty cool. So in this case, I've just come up with 2 of the ratios. Sine alpha over A is equal to sine gamma over C. But we could do the same thing with sine of beta being over B. So this is the stated law of sines. So given a triangle with standard labeling, which is this stuff here, all of these ratios are equal to each other, which is pretty cool, to be honest. Sine alpha over A, that's the same thing as sine beta over B. That's the same thing as sine gamma over C. And of course, you can take the reciprocal of these things and set them equal to each other. So if you're solving for an angle, right, I would go with one of these iterations. If you're solving for a side, then I would go with one of these, because you want the thing you're solving for to be in the numerator. Granted, if you're solving for an angle, that does mean at some point you're going to have to apply an inverse sine, an arc sine at some point. But I think in all my examples today, I'm actually solving for a side. In hindsight, that's maybe not the most encompassing video that I'm going to make, but you know what? I have confidence that you guys can take an inverse sine function to figure out an angle if we needed to do that. All right, so we're going to start off with a pretty plain Jane example. There is absolutely nothing exciting going on here. The only reason I want to do this example is to set up a standard notation, a standard labeling of a oblique triangle to show you how that works, and also that we can solve this, with the law of sines. So here's my standard labeling. I always just do this. I don't know. A, and then B, and then C. I always make the base of my oblique triangle AC. That's just how I do my stuff. We know alpha is 40 degrees, it's given. We know beta is 60 degrees, it's given. Right? We know C, which is 10, is opposite gamma, which is the angle, that we don't know, although we're going to find it very quickly here. And notice this is an angle side angle situation. We're given an angle, we're given a side, we're given an angle in that order, and I always typically go clockwise in the order that things are given, so I know automatically this is an angle side angle situation. So gamma is almost free, right? We know the internal angle measurement of a triangle is 180 degrees, so let's just subtract the sum of the two given angles, which is 100. 180 minus 100 is 80 degrees. Boom, right? C is, or rather gamma is 80 degrees. Now, okay, when you're solving a triangle using the law of sines, it is imperative that you create some kind of link between a side and its opposite angle. If you cannot create a link of a side and its opposite angle, then you're likely not in a law of sines situation. You're probably doing like a law of cosines or something like that. But specifically for law of sines, you have to have this kind of linked pair because this sets up the ratio, right? We know now that 10 over the sine of 80 is the ratio that we're going to use to figure out B, right? To figure out A. A is being divided by the sine of 40. B is being divided by the sine of 60. That's what the law of sines says. So I always look for a linked pair, right? A side length with its opposite angle, and that helps me set up the ratio. So if we want to find A, notice that it's opposite side of 40 degrees. So setting up the ratio, that's the thing that we know. That's the thing that we linked, 10 over the sine of 80. So then that's equal to, just straight up, by the law of sines, A over the sine of 40 degrees. All you need to do to solve for A is multiply both sides by the sine of 40 degrees. It cancels on the left. So then 10 times sine of 40 degrees divided by sine of 80 degrees is A, which is approximately 6.5. And I would put units there, but there's no units for this thing. I guess I could just say units, but I didn't do that. Okay, that's it. We have A. Now, actually, we have a linked pair here, right? This is 6.5. Like this could also be linked, right? We could create a little chain between these guys. And I could actually use this chain to solve for B. I'm not going to do that because I rounded this number, and if I want B to be as exact as possible, then I'll still use this link, right? The 10 over sine 80, which is what I did, right? So B over the sine of 60, because 60 is opposite side B, 60 degrees is opposite side B. That's equal to 10 over the sine of 80. Solving for B gives us 10 sine 60, because I multiplied both sides by the sine of 60, divided by sine 80 degrees, and we get this, so we are done. Okay, very straightforward. Again, kind of a boring problem in the sense that there's no context, but that's it. Okay, moving on. Now let's talk about something with a little bit more context. So this says that a fire is spotted from two ranger stations that are 4 miles apart. From station A, the bearing of the fire is 35 degrees, and from station B, the bearing of the fire is 335 degrees. If station A is directly west of station B, find the distance between the fire and each station. Now, the thing that we obviously need to tackle first is, what is a bearing? Right? I can hear you asking right through the screen, Mock, what's a bearing? I don't know what that is. Very simply, a bearing is a clockwise measurement away from due north. So it's used a lot in like nautical stuff and aviation stuff. GPS stuff, like bearing is anytime you're working with a compass, basically. A degree away from due north, that's a bearing. Okay, so here's a very quick picture of a bearing of 50 degrees. Notice that first, you're rotating the opposite way of a standard position angle, right? Angles are very typically, right, if they're positive, a counterclockwise rotation. Bearing is opposite of that. It's a 50 degree, in this case, it's a 50 degree rotation clockwise away from due north. So 0 degrees, a bearing of 0 degrees is due north. It's exactly north. Anything off of that, you're rotating clockwise away from due north. So if we go back to the picture, if we go back to the paragraph of information here, right, we got 2 ranger stations. A is directly west of B. So I drew it literally west of B, at least on the picture. Maybe I should draw like a little compass. Right, here's north, here's west. Okay, now it's literally west of B. And then there's a fire somewhere, right? And we're trying to find essentially these distances, right? We'll call this one B, we're going to call this one A. What are the distances, right? Away from the fire in station A, that's B, and away from the fire in station B, that's A. Now, we're given these angle measurements. So away the fire from station A is a bearing of 35 degrees, right? The bearing of the fire, 35 degrees, station A. Okay, the bearing of station B to the fire is 335 degrees. Okay, so I labeled them here. 35 degree rotation clockwise from due north, 335 degree rotation away from due north in a clockwise manner is why I drew it exactly like this. Now, obviously, we don't want these angles. They're not part of the oblique triangle. They're exterior angles that we don't really care about, but we can use them to figure out the interior angles of the triangle. For example, since A is directly west of B and we know the bearing's 35 degrees, we can conclude that angle A is 55 degrees. Okay, I need that. That's what I'm going to need. Angle B, right, beta rather, is a little bit harder to figure out, but notice that we are given 335 degrees, and we also know where 270 degrees lands us. If we're going away from due north, 270 degrees puts us at a westward position. So how much further are we going? Well, to figure that out, I could just do 335 minus 270, and that gets us this internal angle here of 65 degrees. Meaning, if we do 180 minus 55 minus 65, we get the interior angle where the fire is of 60 degrees, and now we have a linked pair. Okay, we have this sine of 60 degrees over 4, or probably I'll use the reciprocal of that, 4 over the sine of 60 degrees. And we're going to use that ratio to figure out the distance A and the distance B, starting with distance B. So B over the sine of 65, because those are opposite, that's equal to 4 over the sine of 60. So we get that the total distance from the station A to the fire is about 4.19 miles. And I'm just rounding to the nearest hundredth there. Just some algebra to get there. Multiply both sides by sine of 60. To find A, right, A over the sine of 55 is equal to 4 over the sine of 60. And again, some quick math there gives us 3.78 miles as the distance from station A. Station B to the fire. Okay, and then we're done. The last example is one where we're trying to find the height of a balloon here. So suppose that 2 friends want to find the height of a hot air balloon. One friend walks 1,500 feet away in a straight line and calls the other friend, on the phone or something. Over the phone, they report the angle of elevation to one another using the measurements below. How high off the ground is the balloon? So I could have put some more information in the paragraph, but I thought I'd just draw the picture and put all the information on there. So this friend tells the other friend, I'm looking up at an angle of elevation of 43 degrees. And then this friend reports back that, she's looking up at an angle of elevation of 47 degrees. Given that they're 1,500 feet apart, we can find this, we can find the height of the balloon here. By the way, how did I know this, right? That's probably your question. Well, what I did is I took 180 because I know this angle here is supplementary to this one, meaning that they add up to 180 degrees. So I did 180 minus 47, which is 133 degrees. Then inside of this triangle, right, I can figure out what this angle is because we know the other two. 133 plus 43 is 176 degrees. So there's only 4 degrees left over to make this triangle. So I was like, okay, well, that's a 4-degree angle. Okay, so this thing's not drawn to scale. Keep that in mind. I think this is way more than a 47-degree angle. This is way less than a 43-degree angle if you're just looking at it. But those are the measurements. It's just not drawn to scale. Now, by the way, you might recall this exact sort of thing that we did back a few videos ago that I titled something like Extreme Right Triangle Trigonometry Example or something. I think we were finding like the height of a mountain. We were on a boat or something like that. And then we went this way like 9 miles or something. And then we had to set up 2 different right triangles to figure out, and setting up a system of equation to figure out what the height of the mountain is going to be. Well, we can now do that without all this nonsense. We don't need to construct right triangles for that. We can actually just use the law of sines. We can use this oblique triangle, figure out what this length is, and then just use the normal sine ratio to figure out h at that point. So that's going to be my plan of attack here. Now 4 degrees is opposite 1,500 feet. So that's the linked pair that we're going to use to create our sine ratio, our law of sines ratio, I guess I should say. And so I'm gonna find this measurement first. I'm gonna find x first. So using the law of sines, we know that x over the sine of 43 degrees, right, because those are opposite, should be equal to 1,500 over the sine of 4 degrees. And then just doing some algebra, we get that x is about 14,665.27 feet. So this friend is that far away from the hot air balloon. Right, we just found a distance through the air, which is cool to know, right? And maybe that would have been a question. But no, this one's about the height of the balloon, not how far this friend is away. But it is cool to know. We could actually even find out how far this friend away is from the hot air balloon, a distance through the air. Pretty neat. Anyway, we're finding h, though. So now we have a right triangle, though, where we need to know the opposite side of the angle. And we need to know, and we already have now, the hypotenuse of that right triangle. So we can just now set up a normal sine function. Sine of 47 degrees is equal to h over 14,665.27 feet. So, solving for h, multiplying both sides by 14,665.27 feet gives us 10,725 feet in the air, which is like roughly 2 miles high-ish. 5,280 is a mile. So yeah, roughly 2 miles, I would say. All right. That is all I wanted to do for this video. We will tackle the ambiguous case, angle, side. Excuse me, side angle in another video. Hopefully this was helpful. If you guys have any questions, please leave a comment in the comment section below. Thanks a ton for watching, and I'll see you in the next one.